Hi, in this lecture I will continue to go over some more examples of rigid body equilibrium in three-dimensional. So the first example that I have is asking us to determine the components of reaction at the fixed support A. The 400 Newton, 500 Newton, and 600 Newton forces are parallel to the X, Y, and Z axis respectively. Okay, so this is one of those cases that are all forces are in X, Y, Z, so it would be better to just use sigma of X, sigma of Y, and sigma f Z. So the first thing that I'm going to do is draw the free body diagram of a doesn't have any name, so we will give it a name, AC. So I will just like to draw my outline just like this. Okay. Then I put active forces, which I have is 600 newtons. I have a 500 newtons, and I have a 400 newtons. Then I have a fixed support. If you remember from previous examples, fixed support does not move in X, Y, or Z, and it does not rotate about X, Y, or Z. So that means we have to put a force and a moment in all direction. So it needs AX and moment of A in about X. It has AY and moment of A about Y axis. It has AZ and it has moment of A about Z axis. Okay, so let's start with forces. I have summation of forces in X direction being 0. Anything that points this way is going to be positive. So I have AX. The only other force that I have that points in X direction is the 400, and that is pointing away, so that's negative 400 newtons. So my AX is going to be 400 newtons. Summation of forces in Y equals 0. Anything that points this way is going to be positive. I have AY. The only other force that I have is plus 500 newtons equals 0. Therefore, my AY is minus 500 newtons, meaning AY in reality should have been the other way. But as I said multiple times, you do not need to go back and fix your free body diagram. And the last equation that I'm going to use is summation of forces in Z direction. Anything that points up is going to be positive, so therefore my A sub Z, and then I have a 600 Newton pointing down equals 0, so A sub Z equals 600 newtons. Okay, so let's look at moment equation. I start with axis A, moment about point A in direction of X, summation of all those equals 0. So that means anything that causes rotation about X axis, anything that causes rotation this way or this way. So if you look, I see two forces that will cause that rotation in X axis. One of them is that 500. So this is my X axis, this is my rod, this is my 500 Newton. This 500 is trying to make a rotation about X axis in this way. First of all, it is negative, because if I use right hand rule, rotation of my fingers with the direction of rotation, my thumb is going to point to negative X. So it's minus. The amount of it is 500 Newton force multiplied by the distance that it has in X axis, which is 0.75 plus 0.5. So 0.75 plus 0.5 meters. The other force that I see is 600 newtons. Again, this is my X axis. this 600 is also trying to rotate this way about x-axis. It is located at a distance of 1 meters from x-axis, and if I use right hand rule, this one is also pointing towards negative, so that's also minus 600 Newton 1 meter equals 0. What am I missing? Oh, I'm missing my moment about x, because I was like, this is not equal to x. There we go. So now it makes sense. So now let me write it back here. About x-axis is going to be 1225 Newton meter, my unknown. Okay, let's think about summation of forces, about summation of moments about A in y direction. So all the forces that will create rotation about y-axis, this way or the other way. I already see that 400 newtons, and I already see that 600 newtons trying to rotate this whole rod around y-axis. So let's see. So I have the 400 at a distance, which I'm going to find it and talk about it, and then 600 at a distance, which I'm going to talk about it. So let's see. 400 newtons. This is my axis y. It's trying to rotate this whole thing about axis y, and this is the distance it has from axis y, which is 0.75 meters. If I use right hand rule, fingers curl with this direction, it's pointing towards minus y-axis. Okay, my thumb is pointing that way. 600 is located there. This is my y-axis. This 600 is trying to rotate this whole thing about y-axis too. The distance that one has to y-axis is this 0.75 all the way to y-axis. So 0.75 meters. Curling the fingers, rotation, my thumb pointing towards negative. So that's minus. Again, I forgot to put my MAY on there. MAY comes from here. That's one of my unknowns. Equals 0. So MAY, I'm going to write it up here, is going to be 750 Newton meters. And the last one that we're going to do is a summation of moments about point A in the direction of z equal to 0. So any of these forces that you see that are trying to rotate this rod about axis z. So first of all, before I forget, let me write this. This comes from my free body diagram right there. MAZ. I don't see any forces that will rotate about axis z. Just let's be sure. The 400 does not make any rotation about z-axis. Nope, it doesn't. The 500, it's pulling on axis z. It's not going to rotate anything about z-axis. The 600 is parallel to the z-axis. It's not creating a rotation. So there's nothing else. So that moment about z-axis is just going to be 0. Okay. Let's look at another example. The windlass supports 50 kilogram mass. Find the horizontal force P needed to hold the handle in the position shown. That should be shown. Find support reactions at the ball and socket joint A and the smooth bearing B. The bearing B is in proper alignment, which means it only exerts force reaction. All right, well, that's good. Only force reaction. It does not develop any moment. But we got to look at ball and socket. So take a moment, go back to my lecture on rigid body and free body diagram, of a rigid body. Ball and socket, as I discussed it there, is fixed in XYZ direction, but it can rotate anywhere that it can or it wants. So if I make my famous table here, X, Y, Z, M, 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 X, Y, Z, does it move in XY direction? No, no, no. Can it rotate? Can it rotate in X, Y, Z if I only look at point A? Yes, yes, yes. So all I have to do is draw a free body diagram, and when I put reactions at point A, is going to be only forces. So let's see. Outline of my shape, put active forces on there. Force of 50 multiplied by 9.8 newtons. Reactive forces. There's a point, or sorry, force P. Bearing B. Let's see. Does this, what kind of bearing is this? Smooth bearing. So that's a smooth journal bearing. So that means it moves this way and it rotates this way. So, and it doesn't develop any forces. So I don't care about this portion of it, about the rotations. Does it move in X direction? No. Does it move in Y direction? Yes. Does it move in Z direction? No. So I need an X direction and I need a Z direction. Ball and socket, XYZ, there's going to be 3 forces, AX, AY, and AZ. So this is my free body diagram in 3D form. So how many unknowns do I have? I have P, BX, BZ, AX, AY, AZ. I have 6 unknowns. Well, good thing is I have 6 equations as well. This is one of those cases that all of the forces are parallel to X or Y or Z. So it's easier if I just use sigma fx equals 0, summation of forces in X direction. Anything that points this way is going to be positive. So let's see. Let's just start from one side and make sure we don't miss anything. AX, keep moving. BX, keep moving. P equals 0. Wow, 3 unknowns. I can't do anything with it. Summation of forces in Y direction being 0. Anything that going this way, I'm going to take positive. So start from one end. I have AY. Keep moving. I don't see anything else. I don't see anything else. So that should be 0. So good. One of them is 0. Summation of forces in Z direction being 0. Anything that points up. So start from one side. I see AZ. Keep moving. I see minus. So this is going to be 490.5. I see a 490.5 newtons. And then I see a B sub Z equals 0. Okay. So I still can't do any of these. So I have to go and do my 3 equations of moment as well. So let me really quick redraw the whole thing. P, BZ, BX. That one is 490.5. AX, AY, and AZ. Okay. So let's just start with summation of moment about x-axis being 0. Anything that is trying to rotate this whole thing about x-axis, meaning anything that is rotating this way. Let's, you know what? Let's take at point A. Okay, so point A. Anything that is trying to rotate this whole thing at point A about x-axis. So basically anything that is pointing up or pointing down, I have to take it into consideration. This 490 for sure is trying to rotate it. 490 is trying to rotate this way. If I use right hand rule, my thumb is going to point backwards. X-axis, the distance between this and point, it's right there, 0.4 meters. The BZ is also trying to rotate about x-axis. So B sub z at a distance of 0.4 plus 0.4, 0.8 meters. The rotation that it's trying to do is this way. So if I use my right hand rule, I'm going to get positive moment, and that's it, equals 0. So I get BZ of being 24525 newtons. For my final answer purposes, I'm going to use 245 newtons. So let's go back and see. Yes, I can put it BZ here, 245.5 or 0.25, sorry. And I will get AZ of 245 newtons. Okay. So AZ, I got 245. BZ, I got 245. Okay, let's see what else I can do. Let's write moment in y direction. Or sorry, about axis y. So anything that is trying to rotate this whole thing this way, okay? AX, AY, AZ, I don't need to worry about it. That 490 is trying to rotate also in y direction. This time the distance for it, it's like this. So it's trying to rotate the whole thing about y-axis. So the distance I need to look at is 0.1 meters. So 0.1 meters. Direction of it is going this way, positive y. The only other force that I see is trying to rotate it about that axis is this force P. This force P is trying to rotate this whole thing back, kind of counter the moment that's created by the weight. And the distance that I care about is this distance, which is 0.2. P, 0.2 meters. Rotation is this way. Right hand rule, my thumb is pointing backwards, so minus equals 0. Do I get P from here? Yes, I do. So P is going to be 245, 2.5. So this number is popular. So my P is also 245 newtons. Oh, I have it here, 245 newtons. I still can't figure out AX or BX. So let's see. And the last equation that I have is summation of moment about z-axis. So anything that is trying to rotate this whole thing either this way or that way. I already see two forces. I see Bx and force P. So Bx, we're done with free body diagram, so I can kind of write on it. So this Bx is trying to rotate this whole thing about z-axis, and the distance that I care about is this 0.4. So B sub z, 0.8 meters. Rotation, I use right hand rule. So if my fingers are curling that way, my thumb is pointing down, so that's going to be minus. The only other force that I see is P, which is the same direction as Bx, so I know that that's going to create same moment because it's trying to rotate this way about the axis. The distance that I have for it is 0.8 plus this 0.2 plus another 0.2. So that's going to be 1.2 meters equals 0. P, I already know how much it is, so I can get Bx of minus 36787 newtons. So my Bx is going to be minus 368 newtons. I got a minus, totally fine. I don't need to go change it back. I got a value of 9 minus, so I have to carry the minus here. It's important. See, the Bx, I got a value of minus 368. That's what I'm going to use when I substitute in this equation. And I am going to get AX of 1, 2, 3 newtons. Okay, that was a lot of work, but at the end, it worked out. So this is something, the moments is something that you have to spend a little bit of time to kind of visualize and make sure that you're not missing any forces or anything like that. So the last example that I have is this one. So member ABC supported as shown. Vertical bar ED has circular cross section is fixed at E. If vertical force of 18 pounds is pushing down on B, find force supported by the cable. Find all reactions at A. Okay. So this was also a very important problem as far as what to draw free body diagram for. Because previously I have seen some students draw free body diagram of everything, E, D, A, B, C, and then there are too many unknowns. I have seen people draw a free body diagram of ED, which doesn't help, doesn't provide reactions. So it's important to draw a free body diagram of ABC. Okay, so that means outline of ABC. See that this part kind of throws a lot of people off, but we don't care because it's irrelevant to our problem, what's happening elsewhere. We only care about ABC. There we go. Member ABC. Then we got to put the active forces on there, which is 18 pounds. And reactive forces, which I have a tension T. And okay, so let's find circular color on point A. If you remember, in previous lecture we had a rectangular cross section, shaft and rod. So this is similar, just a little bit different when it comes to some of the rotations, and you guys are gonna see. So let's see, does this move in direction of X? No. Does this move in direction of Y? Yes. It's circular shaft, circular cross section, so yes, it moves. Does it move in the Z direction? No. Oh, sorry, Y is yes. Yeah, no. Let's look at the rotation. Does it rotate about X-axis this way? No. Does this rotate about Y-axis this way? Yes. Circular. And that's the difference between this one and the one that had a rectangular cross section. Does it rotate about Z-axis? No. So I'm gonna circle to make sure I don't miss anything. So I need an AX, I need an AZ, I need a moment about X, and I need a moment about Z. Okay, that is my free body diagram. So the other thing that I have is I have to find force T in vector format. Force T equals T unit vector of CD. I need another table. C is going to be 6, 0, 3. This is going to be, and these are all inches. So unit vector of CD is T RCD, magnitude of RCD. It is going to result in minus 667I, 667J, 333K. Okay, that is my force T. So my Fx, Fy, Fz is going to be easy. Summation of forces in x direction anything that points this way is going to be positive. I have AX. The only other thing that I have is minus 667t equals 0. I can't do it yet. Summation of forces in y equals 0. Anything that points up is going to be plus. The only force that I see in y is minus 18 pounds plus the j component of t plus 667t equals 0. Okay, from here I get t of 27 pounds. If I put it back up in that equation, 27, I get AX of 18 pounds. Okay. The last equation, let's just use it. Sigma Fz equals 0. Anything that points this way is positive. So I get AZ. The only other force that I see is the Z component of the tension. 333 T equals 0. This I already found to be 27 pounds. Therefore, A sub Z will be 91 pounds for me. Okay. So those are my 3 forces. I still have an X. So these were my unknowns. T, AX, AZ, MAX, MAZ. This I found 27 pounds. AX I found 18 pounds. AZ I found 91 pounds. I have 2 more. So I have to use my equations of equilibrium for moment. And I should be able to find them. So let's see. So let's just start with summation of moment about x-axis. So I've got to find everything that cause rotation in x-axis. First of all, before I forget, let me write my unknown. I'm writing this unknown. There is an unknown on my diagram. That's what I'm writing. Okay. What else is causing rotation about x-axis? Let's look. The vertical component of t. Which is, oh, that's y. Okay, because for a second I was like, why is that negative? No, that makes sense. The y, which is 0.667, 27 pounds. That's my t. That is the only force that I see is causing rotation about x-axis. This is x-axis. This is trying to rotate this whole thing about x-axis. It's located at a distance of 3 inches. So 0.667, should have done the math. 27 pounds at a distance. So this is ty at a distance of 3 inches. So I'm going to use this rotation. Curl my fingers. My thumb is pointing this way, which is negative, equals 0. So MAX is going to be minus 54 pound-inch. So let's go back, minus 54 pound-inch. Meaning the way I drew it on the free body diagram should have been the other way. Last one that I'm going to use, is summation of moment about z. Moment of A about z axis being 0. So anything that will cause rotation about z axis. And here I see at least 2 forces. So first thing, moment of A about z comes from this unknown. This is what I'm trying to find. The forces that I see is the vertical component of the force, which is 0.667 to 18 pounds. The vertical component of T. And there's an 18 pounds right there. Okay. And this is my z-axis. So This 18-pound trying to rotate it this way. This 18-pound is trying to rotate it this way. So if you look, these two are kind of canceling each other out. But let's see if the equation will show us that too. So MAZ, let's use this one first. The 18 pounds at a distance of 6 inches. The rotation, curl your fingers towards this direction. Your thumb is pointing towards plus Z, so that's plus. The other one obviously is negative, so rotating opposite way, and it's also located at 6 inches, equals 0. Those two cancel each other out, and as a result we get moment about Z axis is going to be 0. So if you go back here, that is 0, meaning this rod is perfectly balanced by that chord CD. So because there is no unbalanced forces anywhere, this circular shaft is not generating or not developing any reaction to cancel that effect out. You do not need to go and delete it from the free body diagram. Your free body diagram is what you draw, and these are the answers for the unknowns. That's all I have for you. Thank you.